In this video, I will be talking about periodic solutions which occur in the logistic map. So we consider logistic map. And we know now what we know. We know that it has two fixed points. U1 is 0 and U2 is 1 minus 1 over R. If R is less than 1, then U1 is stable. And generally, we can show that all if we start, if U naught, say, between 0 and 1, then UN converges to U1. So we know what is dynamics in this system for R less than 1. If R is between 1 and 3, then U2, which is 1 minus 1 over R, is stable. And again, if U naught is in the same segment, UN now will tend to U2. The question is what happens if R is more than 3. At plot of our logistic map, UN plus 1. So this is our logistic map, it's quadratic parabola. So what happens if U naught belongs to this segment, then UN also will belong to this segment, provided that R is less than 4. So what to check it, let's see what is value. So if, for example, if U naught equals to half, then U1 will be equal to, we can check it, half times 1 minus half is R over 4. And U naught is less than 1. So what it means, if R is less than 4, if U1 belongs to 0, 1, and if U1 belongs to U0, 1, U2 will belong to 0, 1, and at the end also belongs to the same, and at the end UN is in the range from 0 to 1 for any n. And this brings us to the following problem. Now we can consider our logistic map where we presume that R is between 0 and 4 and U naught is between 0 and 1. So in this case, UN also stays between 0 and 1, and we have bounded solutions. And now we can come to our problem. What happens when R is more than 3? So we have bounded solutions at one hand. On the other hand, we don't have any stable fixed point. And this means that we should see something else. So it's not convergence to any fixed point, but what it could be. And one option would be an option is to have periodic solutions. Scenario is to have two periodic solutions. In two periodic solution, every second value for un in sequence of un is equal to each other. This means that un plus 2 equals to un. And from here we can see that, for example, u0, u2 equal to u2 equal to u4 equals so on equals to n, all even terms in the sequence equal to each other, and all odd equal to each other. And they are not necessarily equal to each other. If u0 equals to u1, we will have, this will be fixed point. Because all values in this set, all even terms in our sequence will be also equal to all odd terms, and this means that all values of u are equal to each other. This would be fixed point. But if u0 is not equal to u1, we have truly two periodic solution. un plus 2 equals to un. Now let's try to expand this story. un plus 2 is r times un plus 1 times 1 minus un plus 1. It is our logistic map. And we know that un plus 1 is given by a similar formula. R times, now un plus 1 is in fact r times un times 1 minus un. This is our un plus 1, this one. And here will be 1 minus un plus 1, and un plus 1 is again r times un, 1 minus un. So what we got? We got un plus 2 equals to this in terms of un. On the other hand, un plus 2 equals to un, and therefore two periodic solution two periodic solutions are roots of equation u equals to r, r squared times u times 1 minus u, it is this term, and times 1 minus ru times 1 minus u. Roots of this equation are two periodic solutions. So this is fourth order polynomial. Fourth order polynomial roots should be, in fact, our fixed points, because our fixed points also should satisfy this equation. We know that two periodic solutions, that fixed points also can be considered as two periodic solutions. Therefore, first two roots are known. What we need to find is U3 and U4. So let's try to find them. So we can divide our equation by U, and we will have 1 equals to r squared 1 minus u times 1 minus ru 1 minus u. And after opening all brackets, we will have the following equation: r cube u cube minus 2r cube u squared plus r squared minus r cube times u plus 1 minus r squared. And this equals to 0. So this is cubic equation, and this can be represented. We know that cubics can be represented, can be factorized. So this, we will have linear term and quadratic. For linear term, we can solve it. We don't know quadratic term. I will put it like a u squared plus bu plus c. But we know what is linear term. Since u1 is 1 minus 1 over r, we can have here u minus 1 plus 1 over r. It's not quite convenient. Instead, we will multiply this by r, and we will have ru minus r plus 1. Easy to see that a should be equal to r squared, because this term times this term should give this. And we will conclude that a is r squared. Also, this term times this should give this. And from here we conclude that c equals to r plus 1. And finally, we can find b. So bu times minus r plus 1 plus ru times c should give minus 2r cube, for example. And anyway, so you can make these calculations and you will find that b equals to minus r squared plus r. For 2u3, 4 are roots of this quadratic, and if we put values of a, b, and c there, we will have r squared u squared minus r squared plus r times u plus r plus 1 equal to 0. And roots of this r plus 1 plus minus square root of r plus 1 times r minus 3 divided by 2r. since U3 and 4 form two-periodic solution, we know that U3, well, U4 is RU3 1 minus U3, and also U3 equals to RU4 1 minus U4. I hope you understand this, and you can double check whether these roots of this also satisfy these two. Can be found in lecture notes 1 on page 13. Now let's talk about stability of two-periodic solutions. So two-periodic solutions are found as roots of U n plus 2 equal to some function of un. And we know how we found it. So it was something like this. Un plus 2 is f of un plus 1, but un plus 1 is f of un. Therefore, we got composite function f2 of un plus 2. And we found two-periodic solutions as roots of this. And stability would imply that derivative of corresponding function, this function f of u, which is f2 of u, derivative of this function satisfies condition for stable at points u3, u capital 3 and u capital 4 by absolute value should be less than 1 for two-periodic solution to be stable. Now our question is to find f prime of u. So we know that f is composite function f2 of u. And to find out its derivative, we will use a chain rule. F prime of u is f prime of u times f prime of u. I will try to explain it. So this would mean that f prime, when u equals, say, to u3, will be equal to f prime of u when u equals to f of u3 times f prime of u when u equals to u3. And we know that this is u4. F of u3 is u4, therefore it will be equal to f prime at u4 times f prime at u3. Consider functions, say y equals to f of x and z equals to g of y. Then you know that dz over dx can be found using chain rule. It will be dz over dy times dy over dx, and this will be dg over dy times df over dx. Now, next point, if let z to be defined by the same function f of y, then dz over dx would be equal to df over dy times df over dx. And if we want to find this derivative at some particular point, dz over dx, when x equals to some kind of x capital, then this will be equal to df over dy, where y equals to f at x capital, times df over dx, when x equals to x capital. Good. And next point would be to replace x by un, y by un plus 1, and z by un plus 2. Then we will have dun plus 2 over dun is df over du when u equals to un plus 1 times df over du when u equals to un. Now we are ready to find derivative of function f of u, which is double composite of function f small. The derivative of f over u, we have found it would be derivative of f small over u when u equals to u3, let's say here, u3 times f when u equals to u4. Derivative of f here. We know that derivative of f is r minus 2ru. Therefore, first derivative will be r minus 2ru3, and second r minus 2ru4. After opening brackets, we will have r squared times 1 minus 2 times u3 plus u4 plus 4 times u3 times u4. Derived earlier that u3 and u4 are roots of the equation u3 and u4 are roots of this equation u squared minus r plus 1 over r times u plus r plus 1 over r squared equal to 0. And using Cramer rule, we conclude that this term is u3 plus u4, and this term is u3 times u4. And now we can put here u3 plus u4 and here u3 times u4. And after putting this, we will get f prime at u3 times f prime at u4 will be equal to r squared times 1 minus 2 times u3 plus u4 plus 4 times u3 times u4, and this will be equal to r squared times 1 minus, now we have formula for u3 plus u4, it was r plus 1 over r, and we also had formula for u3 times u4, it was r plus 1 over r squared. After simplifications, okay, so we take r squared, cancels r squared, we will have minus r squared minus 2r minus 4. All this will be equal to, but after completing squares, we will have minus r minus 1 squared plus 5. Two periodic solutions stable. Two periodic solutions stable if minus r minus 1 squared plus 5 by absolute value is less than 1. And this means 5 minus r minus 1 squared more than minus 1, less than 1. And after simplifications, we will get condition for r. R should be more than 3 and less than 1 plus square root of 6. 1 plus square root of 6 is roughly 3.45. So if r is in this range, then our two periodic solution is stable. Final remark, I forgot to tell it earlier. So u3 and u4, formula for u3 and u4, I will repeat it here. It's r plus 1 plus minus square root of r plus 1 times r minus 3 over 2r. They are real or exist when r is more than 3. So what it means? At r equal to 3, our fixed point u2 becomes unstable, and u3, u4, our periodic solution, occurs and stable at this point. So we will discuss it next time.